Hi, and welcome to the flipped instructional recording for 5.05 free body diagrams. Don't forget to complete your science notebook slide for this lesson. You will be submitting that at the end of the unit for their Part 2 test. So complete a slide each time you complete the lesson. And if you struggle with note taking, listen for the parts of the lesson that I tell you to add to your note pages. I'll also be covering the guiding questions, so be sure to jot down those answers. All right, as we get into the introduction for 5.05, we're talking about forces and free body diagrams. Have you ever wondered how engineers develop safer cars or how they figure out how to build buildings that won't fall in earthquakes? Believe it or not all of their complex work boils down to analyzing forces. You're going to learn the basics of how to analyze forces and how to find an object that will move because of those forces. So here are your keywords. Make sure you're putting the actual definition on your note slide, not just the word. And here are the 3 guiding questions that we're going to be answering today. So the first question that we're looking for the answer will be, what are some examples of everyday forces? So page 1 says forces all around you. Force is a push or a pull that occurs anytime 2 objects interact. This means that there are forces all around you. Sometimes they involve objects in contact, like 2 people holding on to a rope, and sometimes they involve objects that are just close to each other, like magnetic objects. In this lesson, you will look at everyday forces that are only a small part of a much bigger picture. First, though, read about the different kinds of forces surrounding you. So to answer question 1, you can put chemical bonds. These are forces that hold molecules together because of the attraction between positive protons and negative electrons. You have electric forces. If you've ever been shocked by electricity, you know about electric forces. These forces are caused by flowing electrons. Magnetic forces. Every time you use a magnet to hang something on the fridge, you see magnetic forces in action. 2 magnetic objects do not have to be touching to be attracted to each other. Nuclear forces. The forces that hold atoms together are the strongest in the universe. That is why they are used to make energy in extremely destructive weapons. Okay, so a couple things noteworthy on this page is force, push or pull, that occurs anytime 2 objects interact. And then all the types of forces is what I would list. Nuclear, magnetic, electric, and the forces that hold molecules together. Chemical bonds are held together with forces. All right, so that gets guiding question 1 answered, and we're ready to go on to page 2. So looking at everyday forces, you have some more listed here. Objects are interacting with each other and other objects all the time. The interaction between these forces can be grouped into 4 categories. So these you will definitely want to list in your notes. Gravitational, frictional, and then you have forces due to ropes and strings, that's called tension, and forces due to solid objects like chairs and floors providing support. This is called normal force. So we have a lot going on here. Let's take a look first at gravitational forces. You'll want this definition in your notes. All objects are attracted to the earth, so there's always the force of gravity acting on objects. 2 frictional forces. Anytime 2 surfaces are moving or attempting to move across each other, friction is present. And even though air isn't exactly a surface, it opposes motion too, which is called air resistance. So remember, you have these other forces called tension, the force provided by an object, like by a string or a rope, like a tension bridge. And then forces by solid objects called a normal force. And that's the force that a surface exerts on an object. The force is usually perpendicular or normal to the surface and opposite the weight of the object. Normal is when you're talking about physics and a direction, and you'll see that in a lab coming up later in semester B. But the normal, the line of normal, is talking about placement, kind of a directional placement. So different than the word normal when we think of something out of the ordinary, not normal, different meaning there. And so we have this activity that asked if we can figure out which forces are present in these situations. So you've got an elevator rising, a toy car being pushed, skydivers. So if you are able to go through and fill all of this out, then you'll have a good understanding of these 4 types of forces. All right, so what are free body diagrams? That's what we're looking at for guiding question 2. And that is answered on page 3, using diagrams to depict forces. When learning about force diagrams, you saw that scientists draw a diagram using arrows to show the type and size of the force. The object is shown as a small box or dot from which the arrows originate. These diagrams are also called free body diagrams. So we used these in Unit 4. If you remember, you had a part on your lab where you had to draw the box and the arrows. So those diagrams are called free body diagrams. And a free body just means that one object is drawn all by itself, even though that object is likely to be in contact with other objects. This way you can focus all your attention on what is happening to that one object. So think of look at this example here. In this image, you can see a lot of objects. Which object do you look at first? First, look at the car with the kid inside of it. That will be your object. So what does a free body diagram of this object look like? Okay, so you've got the child in the car, and then you have all the forces acting on the car. So that's what that diagram looks like. And it explains it, that the diagram of the square with 4 arrows, one's coming out of each side. The arrows are labeled. The top arrow is F sub norm. The right arrow is F sub ab. The bottom arrow is F sub, and you can tell that's gravity. And then the left side arrow is F sub friction. So this might be a great screenshot to take. So if you can get it to where it takes it with that text box in it, it tells you what all of those things mean. But you can also look at it here. So we looked at the image of the car with the little boy inside, and now it says, what does a free body diagram of this object look like? That's where we saw the squares, and then look at the diagram in more detail. So what are they, and how do you interpret them? This is what it is, how they're interpreted. So this is what we looked at, right? There's a lot of arrows and abbreviations going on. So this is how you answer question 2. So what force points down? That's going to be gravity. So the car is being pulled down by gravity. What's pointing up? Okay, so talking about over here, that's the normal force. This normal force is another name for the support that the ground gives to the car. So the ground is pushing up on the car. So this would be the normal. And then the arrow that points, the force that points to the left. So here, that is the force. This means it's moving. The car is moving to the right. So the force of friction is always going to go in the opposite direction from the direction of motion. So that could be a little bit confusing. You kind of have to think of like a mirror image there. Got to have one force, and then if the object's moving, it's going the opposite direction. And then finally, look at the length of the force arrows. Oh, point to the right. Sorry, I skipped that one. So the arrow represents the applied force. And you will see the applied force whenever someone is pushing or pulling. So that's over here, the applied force. And in this case, the child pushing the car is providing the applied force. So you can kind of figure out how you would label your items. So if the child was on the other side or something like that, you would have to make some adjustments there. So look at the length of the force arrows. And what does that length tell you? So if all of these are the same, that means all the forces are balanced, and that means that the object is not moving right now. So it tells you how strong the force is. And then you can use the length of the arrows to learn about the net force. That means the total force being applied. So in this case, the arrows to the left and the right are the same length, and the arrows pointing up and down are the same length. So what does that mean? That means that the object's at rest, the total net force is 0. Okay, so there's a lot going on here to answer guiding question 2. So hopefully you can get that into your notes and your answer box. And then question 3 says, what is important about finding the net force in free body diagrams? So before we get there, it's practicing looking at these diagrams and figuring out what's happening. So as you look at the following images, make sure you read the caption to understand what's happening. Then draw a free body diagram for each situation. Make sure you consider how long each arrow should be based on which forces you believe to be stronger. Also, make sure you label the forces with their names. So the forces that might be present in each case are gravity, friction, tension, normal, applied, and air resistance. So it would be a very good idea to practice at least one of these and put it in your notes. I know a lot of times it's tempting to just go on to the next page, but it's really asking you here to figure out how to draw these. So the elevator is rising up at a constant speed. Okay, so you would have to draw, remember, just the elevator is going to be the box. Your arrow going up is right. The directional arrow going up is going to be bigger because it is moving. The forces on either side would be equal because it's not moving, left or right, it's moving up. So you think about all of that. And then air resistance, we talked about that as being part of the bottom arrows. So you could go through each of these scenarios and just make sure you have an understanding of how that would look. All right, so practicing those after completing your diagrams, check your work. So this is what the elevator would look like. The elevator is rising at a constant speed. That means the forces are balanced. The only two forces here are gravity and tension. So the arrows in the opposite direction, and they're equal in magnitude or length. All right, so now we're looking at, this is the skydiver, and you've got air resistance and gravity. So he's traveling downward, right? So that's why this arrow is longer. And gravity is pulling him down, so that's why this arrow is longer. He's going downward. And then the air resistance is what's causing him to go slowly and not be dropping. So you could take a look at each of those and make sure you had a good understanding of how those would be drawn out. All right, so this is how we will answer guiding question 3, the net force and Newton's laws. What is so important about free body diagrams and finding the net force? If you can figure out what the net force is from your free body diagram, then you can understand how the object will move. Do you remember Newton's first law? So it's the law of inertia. It means that if there's no net force, or if there's a net force of 0, then the object will not change its motion. So if you see an object moving at a constant speed or sitting at rest, you know that the net force is 0. So that might be something you have to really think about and maybe even put in your notes. I think we were introduced in Unit 4. It was pretty basic understanding, like if they're balanced, then the object wouldn't be moving. But what we need to understand now that we can understand this a little further is that the object can also be moving, but it would be a constant speed. So it's not speeding up or slowing down. It means the speed is constant, and those forces would be equal, kind of like what we saw in the elevator. So that might be something noteworthy for you. And then do you remember the second law? This is force equals mass times acceleration. So if you see an object that is speeding up or slowing down, then you know that there is a net force. And that means that they are unbalanced. So that one may make a little more sense if you're trying to visualize that. And then look at the image and corresponding free body diagram. Do you see which forces are balanced? So all of the arrows look like they're about the same length. Can you tell which force is unbalanced? Do you see that the force of friction is unbalanced? So maybe is this a little bit shorter? And that is why the car is slowing down. So you can get all of this information from free body diagrams. So the answer you can figure out for number 3, why is it important? Because from there you can figure out, if you know the net force, you can understand how the object's going to move. So that's that answer to guiding question 3. So using these to find acceleration. A free body diagram can be used to determine the net force, but how does it tell you the value of the acceleration? Remember that Newton's second law can be written as an equation. Net force equals mass times acceleration. So if you know the net force on an object and the mass, you can figure out the value of the acceleration. So remember, you would have to move the mass over, then divide the force by the mass to get that number. So here's some math. I always encourage you to put these sample problems, even if it's screenshots, in your notes so you know how to work these out. So here it says, when you encounter a force problem, you can use your knowledge of free body diagrams to learn not only what forces are acting, but also the net force and the acceleration of the object. Follow along in the example problem and then test your understanding. So for each diagram, determine the following 2 things. So first, it's asking you to find the net force. And the way you do this is by seeing if the forces up and down are balanced. So in this example, they both equal 8,000 newtons. And then if they are, there is no net force in that direction. So for up and down, they're balanced. So net force would be 0. If they're unbalanced, then you subtract. So here we can see that the force moving the object to the left is stronger. So you subtract those. 8,000 minus 4,000 is 4,000. And that's the net force of friction there, you can see. And then remember that the units are in Newton. Force is Newton, the unit of measurement. So then you find the acceleration of the object. Once you know the net force, right, so we just found 4,000, you can use Newton's second law to find the acceleration. And we're given the mass in each case. So here you can look at the mass is 800 kilograms. So now we know that force is 4,000. So we subtracted those 2 and divide that by 800. And that's going to give us the acceleration in meters per second squared. Okay, so this is just again walking you through the problem, and that gives us the acceleration. So I would definitely put pictures of those in your notes so you know how to do that. And then here's some practice to make sure you understand these free body diagram skills. And if you can go through this and get these correct, then you'll probably do very well on the quiz. So when you do miss one, if you put check and you read that information, that might be something good to put in your notes, because that means it's a concept that you're not really understanding yet. So don't skip these. Make sure you go through, read them carefully, and understand why you missed it if you did. And then finally, wrapping up, this is also a great activity. Just putting some concepts together, making sure that you can plug the words in correctly. Once you do that, take a screenshot of it and put it in your notes as well. So you have a lot of notes you could take for this lesson. All right, so that gets us through the end of the lesson. If we go back and just take a look, we've got notes in, we've got guiding questions answered. So look for our flip follow-up session, And please be sure to email me or come see me in Help Lab if you need any extra help.